Alright, today we are going to study queues. Queues are something like this. So imagine an ATM machine, so automatic teller machine. And there are some customers here in line, in a queue. Okay, and every once in a while, a new customer arrives. And when ATM is open, it's empty, then the first customer in the line will be served and spend some time at the ATM, like drawing some cash or depositing some cash, and then he leaves. And then the next customer is served. And the new customers keep coming. Okay, so that's basically the queue. And there are many variants, like there can be multiple ATMs here. So as long as one ATM is empty, customer can be served at the same time in parallel. Okay. When modeling this queue, we model the number of customers in a queue by the Poisson process. Okay. So if there are n customers, the probability that there are n customers in the queue, actually this will include the customer being served at the server, in this case ATM. So this is modeled by the Poisson distribution, so which we have learned before. So this means the time between two consecutive arrivals of customers. So once one customer arrives, the time before the new customer arrives is modeled by the exponential distribution. So that is, and this also we have learned when we studied Poisson distribution, a Poisson process. And also, oftentimes, the time spent at the server is also modeled by exponential distribution. Let's say this is the density function of the time spent at a server. So it is easy if we can model it by the exponential distribution like this. So this is exponential distribution, and this is another exponential distribution with a different parameter, mu. Okay. Now consider the problem of a single server queue. So let's say there's one ATM and not multiple servers, only one server. And there are customers. So let's say we model the number of customers in the queue, including the one being served. We model this number by the random variable n of t. Okay. And number of customers, including one being served. Okay. And the probability, let's say lambda delta t is the probability that a new customer arrives. Arrives during delta t. Delta t is the time, short period of time. Okay, actually, we should include some higher order term like lambda delta t plus O delta t. But we are going to ignore this anyway. So for simplicity, here I just ignore this term, but we should really include it. And also we need the parameter for the time spent at the server. So that is, so mu delta t is the probability that the a customer spends wait a minute, customer oh, customer, let's say customer finishes finishes in, not customer, a service finishes in delta t. Okay, so with this probability, the customer will leave from the server during delta t. And again, this should also include some higher order term of delta t, but we are going to ignore it. Now, based on these assumptions, very simple assumptions, and also, of course, okay, so based on these assumptions, we are going to set up a set of differential difference equations that governs the probability that there are n customers at time t. Okay, so probability that n customers in the queue at time t. Okay, so as usual, let's consider this probability that there are no customers at time t plus delta t. So how can this state be achieved based on the state at time t? So suppose there are no customers at time t, then what should happen is that there should be no new customers arriving. So that probability will be 1 minus lambda delta t. Okay, no customer arriving. Arrives. So this is one scenario. Okay, since there are no customer being served, because the number of customers is 0, so no customer will leave during that time. Okay. Or there was one customer a while ago. So if there are only one customer, then that customer must be the one being served. So he must leave during delta t. So that probability is, by this assumption, that should be mu delta t. Okay, and as long as this delta t is short enough, then these two cases are all we should consider. Okay, so that's it for 0 customer case. In general, suppose there are n customers at time t plus delta t. Then what should be the possible scenario at time t? Suppose there are n minus 1 customers at time t. Then what should happen is that a new customer should arrive. Okay, and that's it. The new customer should arrive, and so that is lambda delta t. And also, at the same time, the new customer should arrive and no customer should leave from the server, right? So if one is being served, so this n includes this customer. So if he leaves while a new customer arrives, then the number of customers should stay n minus 1. Okay, so that shouldn't happen. So that should be 1 minus mu delta t. Okay, and or there are n customers at time t, and then what should happen? Then in that case, let's see. We could say uh, no new customer arrives. That is 1 lambda delta t, and no customer leaves. Okay. Or actually, there could be another scenario. Let's see. Or let's see. One customer arrives and one customer leaves at the same time, and during delta t. Okay, so these two possibilities can be considered. And or there were n plus 1 customers at time t. And then one customer leaves, that's this probability, and no customer arrives. Okay, so let's see. But if you expand this times this and this, there will be delta t squared. So compared to delta t squared is very small, and if we take the limit of delta t going to 0, then the terms involving delta t squared will vanish. So we can actually ignore this term. And similar here, so this is delta t squared, so we can ignore this term. And if we expand this, there will be one term involving delta t squared, and that will be ignored also. And for this one also, this times this will involve delta t squared, so actually we can ignore this term. So after all, we should have something like, let's see, so approximately by ignoring higher order terms of delta t, we should have n minus 1 lambda delta t and pnt 1 minus lambda plus mu delta t. We ignore the delta t squared term, and pn plus 1 times mu times mu delta t. Now let's rearrange these difference equations, and you should have the following results, and I hope you can derive them. So rearrange those equations and take the limit delta t going to 0. We should have this differential difference equations. So for p0, we have this mu p1 minus lambda p0 of t. And for general n, we have lambda pn minus 1 of t plus mu pn plus 1 and minus lambda plus mu pn of t. So these are the differential difference equations that the Q process should satisfy. And in principle, we could solve these equations to find some explicit solution for expressions for Pn of t. Or we could do some simulations based using computer programs. But here we take an alternative approach called the limiting process. in the limiting process, we assume that these probabilities Pn of t will reach some limiting state. So that means this converges to some. Let's fix n and take n to infinity. Then we assume that this converges to some constant. So if we plot this graph, it should look like something like this. So this is time t, and for each n, we can plot this probability. Then it may look like, for example, it may oscillate, but if you take long-term limit, then it will converge to some value, hopefully. This is not always the case, and it is possible that it will oscillate forever, or it will diverge to some infinite values or whatever. But if it does converge, then we can apply various techniques to analyze the behavior of this system. So, for example, if lambda is greater than mu, then what happens? So this implies that customer will arrive at a faster rate than the customer leaves from the server. So that means the queue will grow infinitely larger and larger, and it will explode. And if mu is greater than lambda, then the customer will leave the server at a faster rate than the rate of customer arrivals. So then the queue will shrink, and it will eventually converge to zero, hopefully. And at some point, there will be some balance, and we'll see how it goes. So let's suppose, therefore, this limit exists for each n, not n, so t to infinity. This will converge to some constant that is independent of time. Okay. If that's the case, then this derivative should converge to zero. When t goes to infinity, should converge to zero, because this function is constant, so the derivative of constant is zero. Okay, so if that's the case, then we can replace the left-hand sides of these differential difference equation to zero. So what we have is the difference equation, such as, maybe I should copy this. So let's see. Let's copy this. So we should have this equals to 0 and this equals to 0. Okay, now instead of differential difference equation, we have difference equation. And I hope you know how to solve this by now. And this is just a second order difference equation. So I'll just give you the answer. Skip how you solve it. So that should be this: Pn equals to lambda of mu to the power of n, and p0. And at this point, the value of p0 is unknown. Okay. So how can we determine this value of p0? Before determining the value of p0, let us define a quantity called the traffic density. Just for convenience. So traffic density is basically this constant. So rho, this is Greek letter rho, lambda mu. Actually, if we define S as the service time, and I as the inter-arrival time of new customers. Then this traffic density is this expectation value of the service time over expectation value of inter-arrival time. Because 1 over lambda is the expectation value of this time, and 1 over mu is the expectation value of this service time. So that's what we have in general. Anyway, so this Pn is expressed as rho to the power of n times P0. So, this is probability mass function of the number of customers. So that should imply the sum of all Pn's, n ranging from 0 to infinity, should add up to 1. Okay, so if we substitute this into here, we have n0 rho to the power of n P0, and this is sum of a geometric series. Okay, and this should be equal to 1. Then what is this? So this series converges if the absolute value of rho is less than 1. So in this case, this summation is equal to 1 over 1 minus rho P0. So that's not rho, it's P. And P0 should be what? 1 minus rho. So after all, if we substitute this into this, we have, in general, Pn is equal to 1 minus rho times rho to the power of n. So this is the final result if we assume the limiting process. Now you should check what would happen if lambda is greater than mu, or lambda is equal to mu, or lambda is less than mu. So for each case, what does this imply? Okay, but we're assuming this, so this should not happen. And that's reasonable. From this, the expected length of a queue is given by this. So expectation value of n, the number of customers in a queue is given by, just definition is this, n times Pn. And if you substitute the expression for Pn, this one, then after all, it should be this. Okay, so you should find out how you can prove this result. There are many interesting problems we can consider based on this limiting process. One of them is the waiting time. So if a new customer arrives, how long does he have to wait until he gets served? So suppose there are n customers in the queue. So n customers in the queue. And each of them will be served with for ti seconds or minutes, or in whatever unit. So service time of the ith customer is ti. Okay. So the total time the new customer has to wait will be this: Sn t1 plus t2 plus and so on up to tn. right? So n customers are served for each of them is served for this amount of time. So the sum is the total number, total uh, waiting time. And remember, each of these T1, T2, and so on, they follow the exponential distribution. So the density will be given by this, mu e to the power of negative mu t. And if you calculate the moment generating function, so it's different from probability generating function. It's a moment generating function. So the definition is, so moment generating function of ti is expectation value of exponential of t, sti. So, and if you use this density function for the exponential function distribution, then this should be equal to mu and mu minus s. And s is supposed to be less than mu. Okay. Then, if you know this, you should also know that T1, T2 up to Tn, they are independent. Okay, so this is an independent and identically distributed distribution, random variables. So the moment generating function of Sn should be given by this. So that is nth power of this. Actually, if you know the properties of exponential functions, then you should also know the sum of identically independent and identically distributed exponential random variables follow a gamma distribution. So this is actually the moment generating function of the gamma distribution. So its density function is given by this. It's a little bit involved, but you can just look up some table of distributions. And yes, so this should be the density function of the waiting time of a customer. Now you should notice that this is the density function for Sn, which is the waiting time given that there are n customers in the queue. Okay, but usually we don't care about how many customers are there, but we only care how long we have to wait, right? So we want to actually calculate the probability density function for the waiting time irrespective of the number of customers. So let's say this random variable of waiting time irrespective of customers is s. So we want to first calculate the distribution function for this random variable. Then this should be given as this. So when customer number, the number of customers vary from 1 to infinity. So when there is n customers, then we have to wait. The distribution function for Sn is given by this. N is equal to n. So this one is the distribution function of this density function. So that is, the definition is this. This is the distribution function, or cumulative distribution function if you like, is given by that integral from t to infinity of this density function. Okay, this density function. And we know what Pn is. So from the previous result, this Pn here is 1 minus rho and rho to the power of n. So if we put all of these together in this equation, oh, by the way, this equation means this is an application of the partition theorem. So if there are n customers, the distribution function is this. Okay, and if we put these all together, after all, we should have this distribution function of waiting time, irrespective of the number of customers. It's pretty simple. So you should derive this result. It's just putting all together and calculate this summation and integral. And once you get the cumulative distribution function, you can get the density function for this random variable s by taking the derivative. Let's see. The density function of s is the derivative of this probability with respect to time t. Oh, wait a minute. It actually, sorry, this is not cumulative distribution. So cumulative distribution function is not this, but let's see. It's this, less than or equal to t, which is 1 minus this. So we differentiate this probability s less than or equal to t with respect to t. Then we should have rho, what is it? Rho mu 1 minus rho exponential minus mu 1 minus rho t. So this should be the density function for the waiting time. Using this density function, the expectation value of waiting time, irrespective of the number of customers in the queue, is given by this. So from 0 to infinity and t fs of t dt. And if you plug in this expression and calculate the integral, it should be, let's see, rho over mu 1 minus rho. Okay, so try to derive this result. And if you look at this expression, this is actually equal to expectation value of n and expectation value of t. So okay, if you don't remember, this part is this rho over 1 minus rho, and this part is 1 over mu. So this t is the service time per customer. Okay, so each customer is at the service counter for this amount of time on average, because it follows the exponential distribution with the parameter mu. And this n is the number of customers in the queue. So this is a very simple result. Average number of service time, average service time, and times the average number of customers in the queue. So that's the average service waiting time until one gets the service in a queue. Now have a look at this sample path of this queue process. Here, the horizontal axis is the time from some point, and the vertical axis is the number of customers. So this shows the evolution of the number of customers after some point in time. So at first there are no customers, so which is called a slack period. So this is the first slack period. And at time t1, one customer arrives. So now the system enters the busy period. So if the server is occupied with at least one customer, it is in the busy period. So one customer arrives, and second customer arrives in the queue, and third customer arrives, and the first customer leaves, and another customer arrives, then one customer leaves, and another leaves, another leaves. Then the server enters a slack period again. Then at time t2, okay, and then after some time at time t3, another customer arrives. So the server enters another busy period, and so on. So this is the slack period 1, slack period 2, slack period 3, busy period 1, busy period 2, busy period 3, and so on. Now we are interested in the average duration of the busy period. So how can we calculate this based on the limiting process? As in this figure, we represent each slack period by the duration of each slack period by Si, S1, S2, S3, and so on. And the duration of the busy periods are represented by B1, B2, B3, and so on. So using these notations, for example, S1 is T1, and S2 is T3 minus T2, and S3 is T5 minus T4. So T with odd number minus T with an even number, that is one less than that odd number, and so on. And B1 is T2 minus T1, and B2 is T4 minus T3, and B3 is it would be T6 minus T5, and so on. And we are interested in the expectation value of this B, expectation value of BI. And this should be calculated by this. So suppose there are n busy periods, so we have B1, B2, and so on. So its average should be this 1 over n and some all these busy periods. Okay, and then take the limit of n going to infinity. Okay, so this should be the expectation value of BI. And similar for the slack period, we can calculate. Let's call this, instead of this, let's call this B bar. And we can also consider this similar quantity for the slack periods. Okay, and now let's consider this. Let's see, this period, this slack period. So what's the average duration of this period? Now, remember, the customers arrive according to the Poisson process. So the duration of this time from so there are no customers to one customer. It should be it should follow the exponential distribution with the parameter lambda. So this should be equal to 1 over lambda. This is the duration of the inter-arrival time from between 0 and 1 customer, right? So yeah, this should be the case. And remember, the probability that there are no customers is P0. And that was, what was it? It was 1 minus rho, right? And so the probability that there are more than 0 customers is 1 minus p. So 1 minus p is there are more than 1 customers in the queue. So the ratio between these two probabilities should correspond to the ratio between these two averages. After all, the total duration of this process can be split into two parts: slack periods, and busy periods. And the relative length of these durations should correspond to these probabilities. So therefore, let's see, probability that there are 0 customers relative to the probability that there are more than 0 customers should be equal to the average of the ratio of slack periods and busy periods. But this one is equal to 1 minus rho over rho. Okay, so from this we should have, let's see, from this we should have B bar, the average duration of the busy periods, as S bar times rho over 1 minus rho. But S bar is 1 over lambda. And so this should be the expected duration of the busy periods. And by the way, this rho was defined to be, if you remember, this should be lambda over mu. So if you substitute this in, we have lambda mu 1 minus lambda mu. So that is, let's see, lambda will cancel, and mu minus lambda. So this should be the average duration of the busy periods. By the way, in order to derive this result, we have assumed that lambda is less than mu. Otherwise, the length of the queue will grow exponentially, grow indefinitely. So this means mu minus lambda is of course positive. So this is positive, and it makes sense. Now we consider the case where there are multiple servers. So let's see, in the case of ATM, there are multiple servers. So server 1, 2, 3, up to R servers. So there are R servers. And if there are multiple queues in front of each server, then it is just it's the same problem as the single server, but just multiplied by R. So it's not so interesting. So in our case, we consider single queue. So there is only one queue, and as a server becomes free, then customer is served at the server, which server doesn't matter, but as long as it's free, then a customer is served. Of course, if there are some customers to be served. So let's see. So similar to the single server problem, we also consider the service time follows the exponential distribution with parameter mu, and customers arrive with according to the Poisson distribution with lambda t. And okay, so there are our servers. Okay, and the number of customers, including those that are being served, is represented by this random variable n of t, so which can take integer values, including 0. So we should note two different scenarios. If n is less than r, so the number of customers is less than the number of servers, then the probability, if this is the case, the probability that a server, a busy server, that is the server that is serving a customer, becomes free in the duration of delta t, time delta t, is this probability should be equal to n times mu times delta t. Okay, so each server has the probability of becoming free with mu times delta t, and there are n servers that are serving now, so the total probability should be n times mu delta t. And if the number of customers is greater than or equal to r, the number of servers, then the same probability should be equal to r mu delta t, because there are only r servers, so this probability is limited by the number of servers. So, the number of customers served within delta t is limited by the number of servers, so this makes sense. So based on these assumptions, I will just give you the differential difference equation derived from this model as a result, and you should try to derive them based on the same argument as the single server case. So P0 of t, this should be, actually this is the same as the single server case. Mu P0 of t minus lambda P1, actually this should be P1, and P0 of t. And here is something different. Pn is equal to lambda Pn minus 1 and n plus 1 mu n plus 1 t, and minus and lambda plus n mu and mu Pn of t. So this is the case where n is between 1 and r, less than r. And the last one is this lambda Pn minus 1 and r mu. Wait a minute. This should be p here. And Pn plus 1 of t minus lambda plus r mu Pn of t. This is the case where n is greater than or equal to r. Okay, so what is different from the single server case is that this is proportional to n plus 1, and we have n here, we have r here, and r here. So these are the differences between multiple server and single servers. So these N and R, they come because now the system can handle at most R customers at the same time, simultaneously. So that's why we have this. But we have to separate these two cases, N between less than R or greater than or equal to R, because because as long as there are less customers than the number of servers, then the efficiency of this processing customers is proportional to the number of customers. But that hits the limit when the number of customers exceeds the number of servers, at which time we can only process at most our customers at the same time. So that's why we have to separate these two cases. Just like for the case of the single server problem, we also approach this multiple server problem by the limiting process. So that is when t goes to infinity, the state of this system approaches some kind of equilibrium, so that the left-hand side of this becomes zero. So each probability mass function will be a constant for each n. Now we solve this difference equation rather than differential difference equation. Now let's solve these difference equations. First of all, from the first equation, this one, we have, let's see, wait a minute, we have P1, mu P1 equal to lambda P0. And second, in the second equation, let's put n equal to 1. So in that case, when n is equal to 1, let's see, we should have lambda P0. Let's see. So that's lambda P0 and n plus 1. So 2 mu P2. 2 mu P2 and that should be positive, and lambda 1 mu. Okay, so this is plus and minus lambda and mu P1 equals to 0. So we have 2 mu P2 equals to lambda plus mu P1 minus lambda P0. And let's see. So lambda P0 is mu P1. So lambda plus mu P1 minus mu P1. So this will this will cancel, and we have lambda P1. So that's 2 mu P2 is equal to lambda P1. And then put n equal to 2, and the next equation. So n is 2, so this is P1, and this is P3, and this is P2. And let's see. So that's lambda P1 and 3 mu P3 minus lambda and 2 mu P2 is 0. So we have 3 mu P3 equals to lambda 2 mu P2 minus lambda P1. But now lambda P1 is 2 mu P2. So this is actually equal to, let's see, lambda P2. Now you see the pattern. So 2, 1, 3, 2. So next should be 4 mu p4 equals to lambda p3, and so on until n is equal to r minus 1. Okay, so because the second equation holds for this range of n. So at that point we should have what? Let's see, r mu pr equals to lambda pr1 minus 1. And in general, we have n plus 1 mu pn plus 1 equals to lambda pn if n is between 1 and r, not including r itself. Okay, and for n greater than or equal to r, we have, let's see, for n equals to r, we have lambda pr minus 1 plus r mu pr plus 1 minus lambda r mu pr equals to 0. So from this, this r mu pr plus 1 is equal to lambda r mu pr minus lambda pr minus 1. Okay, and let's see. This one is, let's see, what? Lambda pr minus 1 is equal to r mu pr. So this is minus r mu pr. And that will cancel this part. So we have lambda pr. Okay, and for n is n equal to r plus 1, we should have this doesn't change. Okay, so the left hand side should always have r, and mu pr plus 1 no, plus 2, and lambda plus, again here r, and mu pr plus 1 minus lambda pr. But now lambda pr is equal to r mu pr plus 1. So this one is equal to r mu pr plus 1. So this will cancel this part. And we have lambda pr plus 1. So now in general, we have r mu pn plus 1, let's see, and lambda pn if n is greater than or equal to r. So those are the recursive equations for pn's, and let's reduce everything in terms of p0 first. So from this, p1 is expressed in terms of p0, and from this, so if you replace p1 here, we have what? Let's see. We have 2 mu p2 and lambda p1, that is what? Lambda squared p0 over mu. And if you divide both sides by 2 mu, we have 1 over 2 and lambda over mu squared p0. And we can continue this, and we should find, actually this is 1 over 2 and rho squared. Remember, this is defined as rho, and p0. And this can be generalized into this p to the power of n and n factorial times p0. So this holds as long as n is less than r and greater than 1. Okay. And for n greater than or equal to r, you should try, and it should be Pn is equal to rho to the power of n divided by n r to the power of n minus r and r factorial. So this r is a constant, and p0. So we can express all the terms of this probability mass function in terms of p0. And I hope you already know how to determine the value of p0 now. Of course, it comes from the normalization. So if we add all those terms, it should be equal to 1. So just do it, and the result is p0 plus this summation from n from 0 to r minus 1 and rho to the power of n and n factorial and r to the power of, wait a minute, let's see, I think it should be r and r factorial, and this is r is included inside the summation, and r infinity and rho over r, okay, and n. So this should be equal to 1. And so p0 is 1 divided by all these terms. It's not pretty, but that's the result. Anyways, so let's see. For this part, we can put some of the factors out of the summation so that we can carry out the summation of this series, and that will be equal to, let's see, this part. This summation should be equal to what? Rho over r, and r minus over r minus rho. Yeah, this should be it. And so it can be simplified a little bit. So we have, after all, p0 equals to, let's see, this summation. Not infinity here, so it's finite summation. That's what it makes so ugly. And let's see, r, so this r to the power of r is cancelled by this r to the power of r, and let's see, and r minus 1 factorial, one of r's in this factorial will be cancelled by this r, so r minus 1 factorial, and let's see, r minus rho, and its inverse. That should be p0. And now we want to calculate the expectation value of the queue length. But in this case of multiple servers, it doesn't make sense if we include the number of customers being served, because they are served in parallel, so it's not really part of the queue. So when calculating this expectation value of number of customers in the queue, we exclude those being served so that this is calculated for n from r plus 1. So there are at least one more customers than the number of servers. So that will be n minus r and pn. Now this n includes the number of the customers being served. So we have to start from r plus 1 and subtract r from n. Yeah. And this is quite an involved calculation, but but the procedure is very clear. We just use this value of p0, and we use these probability mass functions for this. Actually, we don't have to deal with this case because the summation starts from r plus 1. But anyway, the result should be something like this. So p0, just leave it like this, and rho to the power of r plus 1 over r minus 1 factorial and r minus rho squared. Yeah, we don't explicitly write p0, so it should be easy to derive this result from this expression. So please try this. Next, we consider the queues with fixed service time. So that means every customer being served is served for some fixed time, say tau. And this is a Greek letter called tau. But anyway, so the first question is, what is the probability that there are no customers at time t plus tau? Okay, of course, we are still assuming that the customers arrived according to the Poisson distribution. So this will be split into two cases. So at time t, there are no customers, and no new customers arrive. That probability should be what? It should be, since it's Poisson distribution, so Poisson distribution with 0 customer arriving should be exponential of negative lambda tau. Or there was one customer and that customer leaves, and wait a minute, there was one customer and that customer is served, and no new customer arrives. So the probability that no new customer arrives is still exponential of minus lambda tau. So after all, we have p0 plus p1, and both exponential to the power of negative lambda tau. So, and the next question is, in general, if there are n customers at time tau, what would have been the cases at time t? So there could be 0 customers at time t, and n customers arrive during tau. Okay, so that probability should be what? Since it's Poisson distribution, so it should be there should be n customers arriving. So that would be what? Lambda t to the power of n exponential lambda t and n factorial. Or there was one customer, but during time tau, this one customer will leave. So if there are n customers at time t plus tau, still n customers should arrive. So it should be again the same probability. Or there could be 2 customers at time t, and so one customer is surely leave during time tau, during the duration of time tau, and so if there are n customers, two customers and one customer will leave, so there should be n minus 1 new customers arriving. So that probability should be this lambda t to the power of n minus 1 n minus 1 factorial. Okay, and it goes on. So three customers, you should think about it. And if there was, let's say, n customers at time t, so one of these customers will leave after the service, so there should be one more customer arriving. So that case is lambda t and this 1 factorial. And if there are n plus 1 customers at time t, then no new customers should arrive, and let one customer leave after the service. So that probability should be exponential of lambda, negative lambda t. Okay, so these are the all possibilities that will lead to n customers at time t plus tau. So let's add them all and try to calculate these probabilities. So P0 is this, and so if we plug P1 n equal to 1 into this formula, you should have, so this is n, and this will be up to n plus 1, so there should be P0 times something plus P1 times something, and up to P2 times something. And so from this, you can derive an equation for P2 equals to something in terms of P1 and P2. Let's see. Not quite. Well, anyway, just add them all, okay? So then we should have let's summarize this tau. And every term contains this factor, e to the power of negative lambda tau, and P0 lambda tau n factorial, and r from 1 to n plus 1, and PR t and lambda tau n plus 1 minus r n plus 1 minus r factorial. So this should be the general recursive formula for the number of customers. So again, we use the limiting process. So if t goes to infinity, then we assume each of these Pn of t will approach some constant value, which does not depend on time. So in this case, we don't have any derivatives, but we can just replace these functions of t to some constants like Pn. So let's see. So if for P0 we have lambda tau P0 plus P1. Okay, so this P0 and this P0 are the same thing. And P1, just replace n equal to 1 in this case. So in this case, we should have, let's see, P0 plus P1 and lambda tau plus P2 and P2 same here, and two new arrivals, P2 and one arrival, and P3 and no arrival, and so on. So in general we have Pn equals to this lambda tau n factorial and P2 lambda tau n minus 1 factorial and P n lambda tau plus Pn plus 1. Okay, so we have these difference equations. So how do we solve this now, this time? We use the probability generating function, okay, PGF, just as we have done before for other stochastic processes. So multiply both sides by s powers of s. So in this case we multiply both sides power s to the power of 0, so that's nothing, and multiply by s and multiply by s squared both sides, multiply by s to the power of n both sides, then add them up. So in this case the left hand side will be the definition of the probability generating function, so n from 0 to infinity and Pn s to the power of n. Okay, so these things. And the right hand side, let's see. So we have if you look at the right hand side, let's see, these things are all the same. And first consider those terms that contains P0 here. Okay, so this is P0 times 1, P0 times lambda t times s, P0 times this term times s squared, P0 times these terms times s to the power of n. So that will be, let's see. So the first thing we notice is this P0 and sum over n from 0 to infinity. We have powers of s and lambda tau to the power of n and divided by n factorial, right? So this is 0 factorial, 1 factorial, 2 factorial, n factorial, and so on. So this term, those involving P0, is this. And we can actually combine this power of s with power of lambda tau. So let's see. We should write s lambda tau to the power of n and n factorial. But this term is, look, this is just a Taylor expansion of the exponential function. So this is equal to exponential of lambda tau s. So let's replace it. So this is P0 exponential lambda tau s. So we can combine these two, but let's look at the next term. So next term involving P1. Let's see. So P1. So there's no there's one P1 here, and P1 and P1 and P1 and so on. So It's the same as P0, so we should have the same result here. And let's see, next, terms involving P2. Those should be this one, and this one, and this one, and so on. So we have one s here and two s's here, but the powers of lambda tau is one less than the power of exponent of s. So we put one s out. So lambda tau p2, one s out. Then we should have again the exponential function, right? So just forget about this s and consider this s, and the next term is s squared and s cubed and so on. And this one, the term involving p2 is this. So here's n minus 1, n minus 1. So s to the power of n is here. So take one s out, there will be one s to the power of n minus 1. So, but the summation continues for n from n equal to 1 to n equal to infinity. So it will be this exponential function. So the similar logic applies to the terms involving p3. That should be s squared times exponential of lambda tau s, and so on. So in general, it should be like Pn s to the power of, let's see, n minus 1 and exponential of lambda tau s. So let's see. Let's summarize this result. And let's exponential lambda tau. That's let's see. Okay, we can combine this this exponential with this exponential. So that will be we have lambda tau, so it will be what? Minus lambda tau 1 minus s. Okay, so that will be p0, p1, and p2s, and what, p3s squared, and in general it will be pn sn minus 1, and so on. But if you look at this and compare with this definition of the probability generating function, so if we add one more s here, so let's see. Let's multiply everything inside this bracket by s and divide by s. So divide by s, so we have s squared cubed and n. So this is almost the definition of the probability generating function, except for the term p0 here missing. So that will be equal to lambda tau is 1 minus s, 1 over s, and p0s plus probability generating function of this minus p0. So we add p0 here and subtract it. So this is what we have. Let's see. So the left hand side is of course probability generating function. So let's see. After all, we have this expression. That is lambda tau 1 minus s, and let's see, p0 plus 1 over s and g of s minus p0. Okay. Now we can solve this equation for g of s. Okay, just expand this and solve for g of s. Oh, this is ugly. And we should have this. After all, we should have p0 1 minus s over 1 minus s e lambda tau 1 minus s. So this is the probability generating function, but it contains p0 as an unknown parameter. Okay, and in general, we should have this. So this limit, g of s should approach 1 as s approaches 1. Usually from the left, okay? S is usually less than 1. Not usually, it should be less than 1, and it should approach 1. Then this value of probability generating function should be equal to 1. So let's do this. And so this, if we take the limit s going to 1, this will be 0. And the denominator is actually 0. So we used L'Hopital's rule, L'Hopital's theorem, and we can still calculate this limit. And that should be this, lambda tau, which should be equal to 1. So from this, we can determine the value of p0 as 1 minus lambda tau. So that's how we determine this PGF. So in theory, if we expand this in the power series of s, then we have the probability mass function, Pn. But this is a fairly complicated function, so we don't do that. Instead, we just calculate various expectation values by differentiating this function. For example, expectation value of the length of the queue can be calculated by first derivative of this function. So that should be, so differentiate this function with respect to s and take the limit s going to 1, then you should have this. So let's see. So basically this is this. And the result should be this. I just give you the final answer. So in terms of rho, this should be rho over 2 and 1 minus rho. In this case, you know, the service time is not exponentially distributed. It's fixed. So in this case, rho should be this, 1 lambda times tau. Okay, so tau is the service time. Of course, expected service time is tau because it's constant. Okay, so that's it. And finally, I'll explain the classification scheme of queues. Basically, there are 3 ingredients in the queue process. The first is the probability distribution of arrival. So arrivals. So what kind of probability distribution we use for modeling arrivals? In the present chapter, we always assume that it is Poisson distributed. It was a Poisson process. And second, of course, service time. In this chapter, we usually assume this is exponentially distributed, or in the last example, it was constant time. So it's a delta distribution, so to speak. And third, the number of servers. So, so this determines the fundamental properties of queues, servers. So each of these have names like let's see, G1, G2, and N. So the classification of queues is given by these three parameters. So G1 slash G2 slash N. So in the case G1 and G2 are G1 is a Poisson process and G2 is an exponential process determined by parameters lambda and mu respectively. And if there is one server, then we usually write m lambda slash m mu slash 1. So this is the problem we have considered in the first part of this first section of this chapter. This m represents Markov, okay? M for Markov process. Okay? And if there are multiple servers, we of course replace the last one with n. Okay? And in the last case, we have examined the case where the service time is fixed. In that case, we write m lambda slash d tau slash 1 server. So D means deterministic. Okay, so D means deterministic. So that means, tau is fixed. So this is how we express, we name a queue process. And that's all for this chapter. See you next time.